Now I want to quickly go through 3 topics related to sorting. The first one is called selection. Suppose that you want to find the kth smallest item or key in a list. In other words, to put it a different way, you want to put the item that would be at index J if the list were sorted where J is k minus 1. So I want to find the kth smallest item for an arbitrary k in a list. The easy way to answer that question is sort the list. We know a bunch of sorting algorithms now, and just pick out the item at index k minus 1, and that'll be the kth smallest item. But can we do it faster? Can we do it faster than sorting? Sorting usually takes n log n time. We'd like to beat that. So if we don't want to do that, then this is a problem that is called selection, selecting the kth smallest key fast. And a really common example is finding the median of a set of n keys, in which case you're looking for keys. You're looking for the item whose index in the sorted array, if you had the sorted array, would be the floor of n over 2. This is something that comes up very commonly in statistics. You have a list of statistical data points. You want to compute the median. How do we do it fast? We are going to use an algorithm called quickselect, which is a modification of quicksort. So we take the quicksort algorithm as we've seen it, and we make some small changes. The most important change is that whereas quicksort calls itself recursively twice, quickselect will only call itself recursively once, either on the left partition or the right partition, but never both, and therefore it will be faster than quicksort. Quickselect is going to start exactly the same way quicksort does. You start with an unsorted list, which I will call I, of n input items. We will choose a random pivot from that list. We will partition that set I into 3 different lists, I1, IV, I2. Remember that we're doing this exactly the same way we did during the lecture on quicksort. So all of the keys that are less than the pivot go into list I1. All the keys greater than the pivot go into list I2. The pivot itself goes into this list IV. Keys that are equal to the pivot can go into any one of these 3 lists. Again, we're going to use the same methods we used in the quicksort lecture. So we'll do one thing for linked lists. We'll do a different thing for arrays. But this step is exactly the same as quicksort. Nothing has changed yet. So items with the same key as the pivot can go into any of the 3 lists, but the pivot itself has to go into IV. Now that we've finished the partitioning step, which is the hard part of quicksort, or at least the part that takes the most time, the only thing that changes is how we handle the ending. And at the ending, as I said, we're only going to call quickselect recursively at most once instead of twice. So what we do is we have these 3 lists. We figure out which of the 3 lists contains the index that we're looking for. So the first thing is figure out if it's in the first list. So the first list is called I1. This notation here means the cardinality of I1, the number of keys in that set I1. If index j is less than the number of keys in that set, then we know that that set is where we'll find the item with index j. And so we will call quick select recursively on I1. And then we'll return that index. Well, we'll return the item, actually. Otherwise, if the index j is big enough that it's not in the first list, maybe it's in the middle list, the list of keys that are equal to the pivot, or at least the list that contains the pivot. So if the index is less than the length of the first two lists combined, then we look in the list IV, but everything in the list IV is equal to the pivot. So let's just return the pivot. If neither of those two cases are true, then there's a third case where j is bigger than that, and therefore the index that we're looking for has to be in the third list of keys that are greater than the pivot. And so we recursively find the index in that list. And we have to adjust the index accordingly because the index will be different in the last list. And that is the code. Any questions on that last part? So again, the main insight here is that when you do quicksort, you have to recursively sort both halves of the partition. When you do quick select, you only have to look in one half of the partition, the half that contains the index that you're looking for. And that's going to make this faster than quicksort. In fact, we can prove, and I may have a chance to talk about it later in the semester, that if your random pivots are reasonably well chosen, then the average running time of this code is linear. By the way, this algorithm really is the code that virtually everybody uses in practice when they need to do median selection or other selection fast, because it really does work well and works fast. It's randomized, so all we can say is that it runs in linear time with very high probability, but that's generally good enough in practice. Any final questions on this? Yeah. What's the alternative algorithm? Oh, well, I mean, if you quicksort the entire list, it's pretty much always slower. So, I mean, the difference between quicksort and quick select is, when you do quicksort, you have even in relatively small examples, you'll have a tree that looks like this. If the index that you're looking for is here, then you don't have to sort this part, you don't have to sort this part. Quick select just does except in the smallest examples, strictly less work than Quicksort does. Oh, sorry, louder? Well, then the question gets complicated. I don't know where the trade-off is there. You would want to experiment and find out.